There we go, that's recording. Okay, so basically what we're going to do, we're going to use these multi-image photographs of collisions and explosions, and we're going to demonstrate that the law of conservation momentum actually applies. Now I think from memory, there's 3 of these, and one of them doesn't actually quite match, but I'll do the first one slowly, and then we'll just we'll breeze through the second one and the third one. Okay, but basically the L.O.C.O.M, as we'll just use it, is total initial momentum should equal total final momentum. That's L.O.C.O.M. Law of conservation momentum, for those watching in the future. Okay, so you also notice that you've got some differences between the masses. Okay, so this one's 2 kilograms, and this one is 1 kilogram. Now, so this is a multi-image photograph, so each of these pictures are taken in even time intervals. So basically, the motion of one part to another in the photograph, need my pencil instead. So just drawing a vector across from those two would accurately represent a velocity vector. Okay, but in momentum, you have to think about the ratios. If they're all 1 kilogram or all the same mass, you wouldn't have to worry. They would be the same in ratio. But, okay, think about it. Remember, momentum equals mass times velocity. So if you've got, okay, if we represent a transition from that picture to that picture, that could represent the velocity. And likewise here, after the collision for the other puck, and after the collision for the first puck. Now, the puck that was moving initially has 2 kilograms of mass compared to the other one has 1 kilogram. The way that we resolve that as a momentum vector is basically we're going to draw across 2 intervals. Does that make sense? Because it's basically 2 times the velocity vector, yeah, compared to 1 velocity vector. Now, in theory, you could, so long as you can make it as long as you like, so long as you had enough pictures and you kept it in ratio. Does that make sense? Yep. Okay. If there's any questions, shout out, as I'm doing many things at once here. All right. So what are we going to do first? Is we're going to draw some momentum vectors. So I'm just going to go straight to the momentum vectors and draw 2 across. Okay. All right, so we got that. So that's actually the system initial momentum, because there's only one object moving at the start. So if you kind of follow what's going on in the picture, you've got one body collides with a second body, and both bodies move off in different directions. Okay. Now let's also draw this one. All right, so there's that vector, and for this one, I'm only going to join up the first with the adjacent. As such. Okay, now, all right. So everyone's happy so far. We've got the initial momentum of the first body and the final momentums of the other 2 bodies. Okay, so now we want to demonstrate that law of conservation momentum is happening here. What we need to do is basically we need to add the final momenta. All right, the way we do that is I think I drew this other one a little bit better, I think, than the first one. Now that's exactly 2 centimeters long. So if I can get that parallel, I'm going to draw it at the end, or maybe even the start of the first one. Yes, I think what I'll do is I'll take this vector, I'm going to move it to here, so I have a vector sum. So I'll demonstrate that. Okay, now the trick of getting parallel vectors. Okay, so you need to set up your ruler and your protractor like such. If you want to move it to the other side, you can actually kind of set up the arrangement, so you move your ruler across and put it on the other side. Actually, that might even be better for this instance. Okay, so either way. So you get the idea. Basically, I'm going to look over my ruler and geoliner and line that up so it's parallel. Now, all I can have to do then, so I'm just going to make sure I get that right, is I'm going to shift that ever so gently so that's sitting right over the end of that vector. Now I'll leave enough space for, put a pencil line in, just going to draw a very, very soft line. I can even just mark out a couple of dots if you've got enough, if you don't want to draw the pencil line. Now, so now what I've done is I've drawn a parallel line to that vector that I was copying. And now all I've got to do is draw a vector that joins it up. Now that was 2 centimeters, yes? So I'm going to draw that, follow that direction, 2 centimeters. Okay, now I'll translate that vector over, and I'll just join up from start to finish. Okay. Now I've drawn that arrow a little bit too big, so it kind of goes over the dot that I'm using for the point where I'm terminating my vector. So that dot and the center of the cross help find the position where you're going to start and end your vector. So you want to start and end at the same point on the object, because the object's larger than there's a single point. But in any case, I can just measure that. So that's about 3.4 centimeters or 34 millimeters. I'll measure the other one. It's the same. Okay, but that doesn't necessarily prove anything. What I should do is line these up. I can actually use the geoline itself because it's got a lot of parallel lines in it. So I can line that up. Okay, I've got a parallel line, and yeah, the other one's roughly kind of fitting that parallel line. If I can kind of just keep that. Yeah, the direction is very close. You guys might not be able to see that, but hopefully in your own, you can observe that as well. All right. So, people able to, you might still be working on your own, but people get the general idea what we're doing here. So I'm just a rehash. I'll just go through the other ones a bit quicker. All right. I'll just move this up. Okay. All right. So the second one, we've actually got 2 bodies coming in and colliding. So this one's a little bit harder. Now, also pay attention to the ratios. We've got 2 to 6. So the ratio of masses is 1 to 3. So you could do 2, and if there's enough space, 1, 2, 3, 4. No, there's not. All right, so then you must do one velocity, and then 1, 2, 3 velocities, such that you have the right momenta. Okay, because that's 3 times the mass of the other one. So you've got to keep get the momentums correct by going over just as many velocity frames. Because remember, the adjacent frames are just a representation of the vector of velocity, a scale diagram of velocity. Momenta, you have to look at the ratios of the masses. All right, so let's draw that first velocity vector. Actually, this is also the momentum scale vector. And we'll draw one over here as well. Okay. All right, now the ones we draw here, now you just got to be careful with where you draw to. See this point here, doesn't quite, I think it's part of this journey, the journey in, and then everything there onwards is part of that. Just be careful, kind of like, does it occur before or after the collision? The way to kind of avoid that is just by picking sources near but not where the collision occurs. So Now, I'm joining up 3, so, and that's 3 transitions. That's not 3 pitches I'm joining up, so that's actually 4 pitches. I'll show you what I mean. So this needs to be 3 velocity vectors to make the momentum correct. So 1, 2, 3. So 4 pitches are joined up, but it's 3 velocity vectors making the momentum. All right, likewise. Okay. So 1, 2, 3, and that's going towards the collision. All right. Okay. So at the top, we've actually got, these are both our finals, and these are our initials. Now, there's a couple of ways that you could demonstrate the proof. You can essentially find the change of the momentum of body A and the change of momentum of body B. That requires negative vectors. So I think we just go with what we did before, which was total PI equals total PF. All right, which means you have to add the ones on the top and the ones on the bottom. Because that's on the bottom is the system before the collision, on the top is the system after the collision. All right. So again, let's translate some vectors. All right. Actually, yeah, I can do that. All right, I should measure this beforehand. I'll remember it. All right, that is exactly 2 centimeters. All right. Oops, that's the way to go. All right, so get that parallel. Sorry, let's turn this so you guys can see it properly. That's better. What's that, parallel? Yep, it's parallel. So make sure your ruler doesn't move when you do this. The ruler is the guide. I just moved then, but I've got my geoliner in place anyway, so it's fine. The ruler is the guide to make sure that you keep this parallel. So soft line for now, and then I'll put onto there 2 centimeters in that direction. And that's the scale of my momenta. Okay. There we go. And we can join the start to the end. While I'm doing that, I'm also measuring it. It is 44 mils. Okay. So that's the initial. So there's actually no numbers for the velocity, so thereby you can't actually have a numeric scale. You could express a ratio in terms of V, I suppose, but other than that, you can't actually know exactly what the ratio is. That's kind of the point. If you could do that, then you could probably work it out mathematically. All right, so that's before, and now we do after. Okay, turn that back around. So I think for the sake of just being able to compare them easily, I'm going to move that one over to there so it's closer to the other one. All right, so let's move that across. All right, how are we going to do that? Okay, I can do that, so I'm going to move that up. Okay, so pivot that around till you get the right direction and shift it up. Okay. Soft line. All right, I didn't measure that. That is exactly 25 millimeters. I've drawn this the wrong way, I just realized. That was silly. I realized my mistake. This one's meant to go, I did the wrong direction. 2 centimeters that way. No one call me up for it. Sorry, that one's wrong. Yeah, I drew the initial momentum vector in the wrong direction. That's right, everything seems to be working so far. The technology's working, so I'm not sure if you all got your hands up furiously over there. You're staying quite quiet. Okay, so yeah, there we go, because it's completely the wrong direction, so that clued me into the fact that I'd done something wrong. All right, so I'll just erase that in a minute. Okay. All right, so there we go. So let me just erase that, so save myself an embarrassment. Okay, so those are a bit off. That's the one I feel that just doesn't work. Maybe you, if you guys have tried that, maybe you had some more success with that one. No, that one doesn't seem to work. I knew there was one on this sheet that doesn't quite work out right. So it's, I mean, you can look at the magnitudes, but the directions are obviously off. And even just doing that quickly, I shouldn't get that sort of mistake with the direction. Obviously, I did still follow the parallel line. So that's 2.5 thereabouts, and that's it's actually about the same magnitude, but it's definitely the wrong direction. So it's so the idea on the top of the sheet says show that momentum is conserved in each of these collisions. This one is not. So total pi does not equal total pf, because even if the magnitudes were exactly equal, the direction is certainly not. One goes kind of like slightly up, like north little degrees towards the east, and that one's north a bit more towards the west. Okay. You guys happy so far with this? We'll go through the explosion one. Now, see this one on the bottom here, that's our explosion. So we've got the following represents explosion where stationary object breaks up into 3 pieces of mass m, 2m, and 3m. So in this case, we don't even have the mass, but we have a ratio of mass, and that's good enough. So, all right, so then they label them. So that's mass, that's got mass m, that's 3m, so that's moving, that's a big mass moving away slowly, and the 2m, larger than m, but it's moving away faster than the 3m, but slower than the 2m, sorry, slower than the mass m. Okay, so we just do that in ratios as well. So the easiest thing is just to go, okay, 1 velocity vector represents the momentum vector, 2 velocity vectors represent the momentum vector, and 3 velocity vectors represent the momentum vector here. So let's draw those. Okay. Okay, 3 for this one. So 1, 2, 3. Okay. Oops, measure it from there. Just measure the length of these for now. I'll say that's 27 mils. Okay, in the final one, you need 2 of these. Okay, that's very close to 3, but slightly off. It's not quite as well drawn as the other 2. Okay, so that's 3 centimeters actually, 30 millimeters. All right. So the idea is, so the total PI equals 0. And then PF is the sum of, is also 0, but it's the sum of the three vectors. So what I could do is, so PF, total PF, by law of conservation momentum will be 0, but it's the sum of the three bodies. So if I call that kind of A and B and C, maybe I should have done them. I'm going to do them in the order of masses. So A is mass 1, B is mass 2 units, and C is 3 units of mass. So some organization with that. So, okay. But anyway, it's the final momentums of A, B, and C must equal 0. Okay, how do we do that with some sort of vector diagram? Well, okay, I mean, you could add all three together and show that it forms a closed loop, or just rearrange that. You can add two of these, and then basically see that it becomes the other. For example, if I move the C across, so minus PC equals the sum of the other two. Okay, so if I add A and B, then I should get C in the other direction. It's a bit unfortunate I wrote in that space because that's actually where I'd probably draw it. To tell you what, if I just swap that around, I can swap the signs. So I can make that a positive. I'm purely changing this just for the sake of just drawing space, if nothing else. All right, so that's going to be positive equals minus PA minus PB. So if I draw A and B in the opposite directions and add them up, it should be equal to that vector. All right, so basically, now I've got A here. So it's running up that way, so the negative will run down that way. That way. And then this will run down in that direction. All right, so I just need to translate this one and then run it in the opposite direction with the same length on the end of this one. And I should have the same as this. So let's see how that works. So is anyone confused by that? You can try it your own way. Just follow along, see how I go. Last one I'm going to do. And then you guys can, you can practice this yourself, or you can work on some of the other momentum stuff. So let's translate this across. Okay, it's always a bit tricky working out which way you need to put your protractor. Okay. Just need to get this parallel line. All right, so let's move that across here. Draw a soft line. And take your ruler away then. All right, that was 30 mils, or thereabouts. Okay, now so what I got there, that should be the same as the momentum of C. That going that way in that direction is minus PA, and that's going that way is minus PB. So I've completed this equation: minus PA minus PB. So I've added those two. Is PC. Now let's just check the direction. It's a little bit tricky. I can do it the same way as I translated it. All right, just move that up. Let's see the direction. I can just swing this through and just have a quick check. It's a little bit off. So you can see that it's not quite parallel. Maybe it's a little bit hard to see on the screen, but I can definitely see it looking overhead. It's a little bit off and it's a little bit short, but look, it's pretty close. So you can try it a different way if you'd like. You could add all three of them and see that they form a closed loop. That's vector A, vector B, vector C equals 0. Or you can do some other arrangement of adding, like add the negatives of B and C and see if it equals A, or some other variation thereof. There's probably about 6 or 7 different ways you could demonstrate this, but just by rearranging the equation. All right, I'm just going to turn off the recorder.